Thanks, Tamar. That was a nice talk.
Thank you.
Anyone got any questions? So I suggest that you put your hand up in the participants list. Stephen, question? Should be able to unmute yourself. Let me know if not.
Yes, there was a question about the. It was a slide you showed in the middle about the BISTABILITY.
Yeah.
And yes, that's exactly it. So on the right-hand side, you have that picture of the energy in the 2D and 3D modes.
Yeah.
Maybe it was the next slide. Yeah. So there's a long period oscillation.
Yeah.
In the 3D component of the energy.
Yeah.
So is that linked to the delta omega from the final part of the talk? I was wondering.
So that's
something else.
That's a bit different. It's actually what happens here is, oops, sorry. How am I going? There is no going back. So it's a bit different here when you have the. Okay, I'm gonna do it this way. When you have the geostrophic mode that grows, you have a strong detuning by advection of the waves, and that kills the transfer of energy from the tidal flow to the waves. So you kill the transfer of energy from the tidal flow to the waves, but because the geostrophic flow are rather large scale, they persist for a very long time, and you have to wait for the geostrophic flow to dissipate a bit for the wave to be able to kick in again. It's not okay. It's not entirely clear on this picture, but there are some other simulations where you can clearly see this kind of predator kind of behavior where geostrophic mode kicks in and it kills the waves, it kills the instability, and you have to wait for the geostrophic mode to settle down to be able to have the instability again.
Okay.
And surprisingly, we didn't really see that in the simulation, in the experiments. I think the reason why is because in the simulations, we had quite localized vortex at the center. So you could still have the wave existing outside this vortex. So you could still have energy transfer through the resonant mode outside the vortex.
Okay, thank you. Thank you.
Steve, I think you were next.
Nice talk, Thomas. So I was sitting all the way through your talk and you nearly answered the question that I had right at the end about the random superposition of inertial waves.
Yeah.
So yeah, Moffat's paper says, yeah, if you have a random superposition, then you need some kind of breaking of the symmetry to get, say, an alpha effect or something. So
yeah.
Yours aren't randomly forced. They're not a random superposition. So do you ever see a net helicity in your?
So to be honest, I've never checked the net, whether you have a net helicity in the wave turbulence.
What about in the geostrophic case?
I'm not sure. There is in the simulations there is clearly a bend towards cyclones. I'm not sure that tells very much about the helicity though. Yeah, to be honest, I don't think I'm able to say anything about the helicity in this setup.
Yeah, it might be worth looking. You can get symmetry breaking to these states with net helicity.
Yeah, and so what Benjamin and Michael were thinking about is if you manage to have some sort of sweet spot where you still have waves but geostrophic flow, possibly you can break the symmetry between prograde and retrograde waves, but I think that's still unclear.
Okay, thanks.
That's definite. I think you're next.
Okay, thank you. Nice talk. I wanted exactly on this slide. So we're talking when I see geophysics, and so I'm not really an expert about wave turbulence, but here we're talking about a particular mechanism that is forced by libration, right?
Yeah.
So when you say geophysics, are we talking mostly about moons, actually?
Yeah, exactly. Yeah. Okay. So moons that are too cool, that have cooled too much to be able to drive thermal convection, typically. Like Ganymede and Io are too small to drive. Well, Io is a bit complicated, but Ganymede, for instance, is too small to have still a magnetic field that is driven by convection. Yeah. Sorry. Okay.
No.
And you wanted to say something else, perhaps?
No. Just so basically, we don't really expect planets to be there, right?
So that's quite unclear. For instance, as far as I know, it's really hard to explain the Earth's magnetic field before before 1 billion years ago, because you don't have the growth of the inner core, and without that, for some reason that I don't exactly understand, it's quite hard to explain like convective dynamos. I'm not entirely sure about that. Maybe someone in the audience will be more experienced on that. So that it could be also a mechanism that is interesting for young planets that have, like especially in the case of the Earth, where in like say 3 billion years ago, the moon was much closer to the Earth, so tidal distortion was much larger, and possibly, well, there was convection, maybe there wasn't, so that's not clear, but clearly tides were, well, maybe tides were doing something, and maybe wave turbulence has something to do with that. But yeah, to be honest, there is still much work to do to be fully describe a geophysical setup. That's more like work for the future, to be honest.
Thanks.
Chris, you had a question as well?
Yeah. It's about this appearance of the geostrophic modes, yeah. As I understand it, the whole system is driven by these inertial resonances, yeah. So, and you're in your wave turbulent regime, everything is time dependent, yeah. So basically, you've got a collection of waves, everything has a time dependence. And then suddenly, when your forcing is sufficiently strong, yeah, you suddenly get to this regime of geostrophic behavior. Are these geostrophic modes actually exactly zero frequency? I mean, do they oscillate slowly, or do they just sit there forever?
Okay. So I think I'll try to answer to this question by going back to, I think, this slide.
Yeah.
So the fact that you can have so they have, what we see is their frequency is really centered on 0. Okay, so we don't have enough, say, maybe not enough time resolution to spot very, very long oscillations. Well, although you can see, for instance, in the no friction case here, that you have some like long oscillations, but here they are more driven by the fact that you've killed the supply of energy by detuning the waves and killing the resonance. So it's more that that drives the variation of that is able to drive the variation of the geostrophic mode than.
So should we be thinking in the geostrophic modes of a sort of band of frequencies centered on very low frequencies? Is that perhaps more correct?
Yeah. So it's
rather than actually exactly 0. I mean,
that's. I completely agree with this comment. In fact, you can't discriminate between waves and geostrophic modes when the frequency is smaller typically than the Rossby number. Yeah, no, that's absolutely right.
Right.
And in these simulations, so that's a further hint that friction can be important. In these simulations, the 2D modes are are the only one to because we don't have sufficient box height. Those 2D modes are the only one to have to satisfy the small frequency limit. So that's why they play they seem to play. So that could be part of the reason why they play such a particular role in those simulations. Yeah.
Right. Okay. I mean, I'm just trying to understand it. I mean, so in a sense, what you've got almost is a sort of cascade towards very low frequencies. That's really what's happening, is it? I mean,
so
is this understood really as to why you get these cascades? I mean, there's all stuff about cascades in wave number space, which is sort of fairly well understood in sort of rapidly rotating systems, but this sort of cascade towards very low frequencies,
so
I'm not so familiar with it.
So I think that's in the geostrophic saturation, what the instability that I've described does is really there is no cascade. It's really you have one wave that has a finite frequency, and it directly directly puts energy into the zero frequency or almost zero frequency modes, right? So there is no progressive cascade. In this case, there is no progressive cascade towards smaller frequencies.
Yes.
But what's quite interesting and possibly puzzling is that, so let me find the right slide. In this case, so if you look at the spatiotemporal spectrum, you tend to put more energy towards smaller frequencies. And in fact, local interaction, as you expect, roughly in turbulence, they give you an isotropic transfer towards smaller frequencies. And I agree that it's quite unclear, why does it change? Like if you allow the geostrophic mode to be back, why in this case you can jump from the finite frequency of 1.5 and directly go to 0, and in the other case you can just go continuously towards the smaller frequencies. Yeah, I think that's not entirely understood.
Yeah,
at least
really
by
yeah. There's a lot to do here, isn't there?
yeah, there is. Oh, that's I think a very exciting problem.
Yeah, it's a very good talk. Thanks.
Thank you very much.
Oh, Stephen, you had another question?
Yeah, this is. I think this is a simple question for someone who knows about orbital dynamics. So not me. So at the start, I think you explained on physical grounds that the libration parameter f would be 1 for a certain kind of orbit, but then later on you were taking f to be 3 or 4. So to what extent is f constrained by orbital dynamics, and to what extent are you allowed to choose it to be whatever you like?
So I think in complicated planetary systems, like say Jupiter, like Jovian and Saturnian systems, when you have many moons, actually you expect not only one frequency to emerge, but you expect to have more frequencies depending on the tidal interaction, not only with the planet, but also with the other moons that are also orbiting around Jupiter or Saturn. So that's why it's not too bad to choose other frequencies. It's not too unrealistic for geophysics. But as I said here, it's really more a trick to optimize the growth rate and to make sure that we access like more nonlinear states rather than sticking to the geophysical case. And yeah, in fact, when you pick the f equals 1 in the experiments, it's really hard to see an instability because the growth rate is very high, which is quite interesting, in fact, because it means that like you have a strong shift in the threshold of the primary instability at the frequency that is mostly relevant for moons.
So in all the theory you showed at the end, where you had the growth rate sigma, let's say,
Yeah.
With the delta omega and whatnot. I mean, the F doesn't really appear in that, does it?
So
is it hiding somewhere?
So yeah, I didn't discuss that, but if you look at the relation at the bottom, you do have a dependence on the growth rate with the wave frequency, so the resonant wave frequency, and you see that the growth rate increases when the growth rate of the geostrophic instability increases when you decrease the frequency. So that means that the dotted line curve here would be shifted towards the threshold of the instability when you decrease the frequency. Yeah.
Okay, but at the start of the question, I think you said that for these sort of Jovian satellites, you'd be thinking of really that there being several values of F simultaneously.
Yeah.
Yeah. Okay, and it's, you know, something emerges from one of those or something.
Yeah.
Yeah.
Yeah. And then it's very complicated and
yeah,
it's quite hard to conclude a priori.
Okay, thank you.